In this sixth module, we are discussing weak interactions, and in this 10th video we will talk about oscillation between different neutrino flavors. After following this video, you will know how to describe the quantum mechanism of oscillation between neutrinos of different generations and the key methods used to detect such oscillations. You may have wondered why the particles nu-L, nu-M and nu-H, which we have introduced in Module 1, do not appear in reaction mediated by the weak force. The reason is just that, as for quarks, the neutrinos which interact with the W's are superposition of these real particles. Consequently, a phenomenon analogous to quark oscillations happens in the family of neutrinos. Vacuum oscillations between different neutrino flavors can occur if neutrino have a non-zero mass and if their mass is different from generation to generation, and these two conditions are indeed met. Let us first consider two flavors of neutrino, nu mu and nu tau, for example, involved in weak interactions, and two mass eigenstates, two real particles, nu m and nu h, with masses mm and mh. The relation between the two classes are unitary rotations in flavor space. The angle theta mh is the equivalent of the Cabibbo angle in the quark sector, which we have introduced in video 6.7. The two particles, nu m and nu h, propagate in the z direction, for example, with different wave function because of their different masses. The second equation is valid in the ultra-relativistic approximation, where p is equal to e minus m squared by 2e and t is equal to z. Now take a nu mu beam at t equal to 0, created for instance by a pion plus decaying a mu plus a mu neutrino. At a later time t, so at a distance z from its origin, this beam will be composed differently. The probability to find a nu tau in this beam will therefore not be 0. The factor 1.27 takes into account the constants as well as the conversion of units, such that we can put delta m squared, which is equal to mh squared minus mm squared, in electron volt square, E square in GeV square, and Z in kilometers. The two factors in the equation correspond to the amplitude and phase of an oscillation. By choosing a distance Z, which is of the same order of magnitude as delta m square over 4e, one can thus make a part of the nu mu disappear and convert into a nu tau. This nu mu disappearance was first observed for the so-called atmospheric neutrinos. Cosmic rays incident on the Earth atmosphere are mostly protons. The hadron shower they cause in the atmosphere is dominated by pions. In their decay, pions produce nu mu and nu e in a relative proportion of 2 to 1. Thus, there ought to be twice as many nu mu and anti-nu mu in the atmospheric showers than nu e and anti-nu e. If, on the other hand, neutrinos undergo oscillations, the ratio of both neutrino flavors will vary with distance. Fortunately, Earth provides the means to vary the distance between the source and the target without moving the experiment. Neutrinos from the nadir travel a distance larger by the Earth diameter compared to those from the zenith. As the primary flux of cosmic protons is homogeneous and isotropic, and since low-energy neutrinos hardly interact with the terrestrial matter, any change in the ratio of nu mu to nu e with a zenith angle is an indication of oscillation. It is evident from the unitarity of the operation that for the probability of survival nu mu, which stays, and nu mu is equal to 1 minus the probability of oscillation. Experimentally, one averages over the unknown neutrino energy at a known propagation distance. The oscillation curves for different energies, shown here by different colors, are thus averaged over the spectrum of neutrinos. This gives the black curve as a function of distance, indicated on the top scale, or as a function of the angle of incidence, indicated on the bottom. The neutrino flux is measured and the flavor identified by measuring the reaction rate of charged current interactions, which produce either a muon or an electron in the final state. With a known cross-section, the reaction rate is proportional to the incident neutrino flux. One finds experimentally that the observed flux ratio is compatible with the calculated oscillation probability. Please note that the scale of length over energy in this plot is the opposite of the one we have shown in the slide just before. The observed oscillation amplitude is quite large and therefore corresponds to an angle theta h equal to 45 degrees plus minus 13 degrees. The difference of square masses is of the order of 3 times 10 to the minus 3 electron volt square, and thus extremely small. Furthermore, it is more likely that the oscillation of atmospheric neutrinos happens between the second and third generation, that is, between nu mu and nu tau. In general, the relationship between the states participating in leptonic weak interactions, nu e, nu mu, and nu tau, and the eigenstates of the mass operator nu L, nu m, and nu h, is described by a unitary matrix of 3 by 3 elements, analogous to the Kabibo-Kobayashi-Maskawa matrix for hadronic currents. For lepton, it is called Pontecorvo-Maki-Nakagawa-Sakata matrix. Like the matrix for quarks, the one for leptons may contain a non-trivial phase that would violate CP symmetry if it existed. Future neutrino experiments will show its existence or not. Different types of neutrino oscillation have been observed to date, and an exhaustive list is the following: disappearance of atmospheric nu mu, disappearance of the nu mu produced at accelerators, appearance of nu tau and nu e in a nu mu beam produced at accelerators, disappearance of antineutrino HIPO and abundantly produced in nuclear power plants. For each of these measurements, we give here a source of information that you can use to find more details. As an example, we show here the interaction of a nu tau appearing in a nu mu beam produced at CERN and observed by the Opera detector situated in the Gran Sasso Underground Laboratory in Italy. The neutrino interactions are observed using photographic emulsion, which are then developed. The d by the x of charged particle thus becomes visible. These animations show an enlargement around the vertex of the neutrino interaction. The reconstruction shows in the final state a charged tau lepton in red, which decays into a pi minus in sun, and a pi zero, which is invisible. The kink between the parent and daughter tracks is a clear signal of a tau lepton decay. The photons from the pi zero decays are shown in yellow, and they point to the decay vertex. This topology is a clear signature of a nu tau interaction, which had appeared in the nu mu beam by flavor oscillation. Neutrino oscillations are a very lively research sector in the United States, Europe, and Asia, and we can expect spectacular results by experiments which are in progress and under construction. In the next video, we discuss the fact that mass is not an intrinsic property of particles, but it is dynamically generated by the Higgs mechanism.